Today, I would like to continue talking about the concept of partial fraction expansion when it comes to um, its application in finding the inverse Laplace transforms of various functions. So if my memory serves me correctly, which could be wildly wrong, you guys know that I can't remember anything. I believe in our last class meeting, we had covered the case when we had distinct real roots, and that is literally it. The first thing that we're going to look at today is then what happens when we have repeated real roots. So let's say that we have a function f of s that could be written as some polynomial in s in the numerator divided by s plus p to the mth power. So we have a repeated real pole that is repeated m times. The partial fraction expansion of this repeated pole is going to look like b1 over s plus p plus some coefficient b2 over s plus p squared all the way out to b sub m over s plus p to the mth power. So this is what it's going to look like. Now we need to figure out how to calculate b1 through bm. And typically speaking, it's easiest to start with our expansion coefficient for our highest order term. So our coefficient b sub m is going to be equal to simply s plus p to the mth power times our original function f of s evaluated at s is equal to negative p, which is effectively exactly what we did for a distinct real root or distinct real pole. Things are going to get a little bit more complicated though for all of our lower order terms. So b to the m minus 1 is going to look like 1 over 1 factorial. I'm writing it this way, even though that is obviously just the number 1, so that we can see the pattern that's going to emerge on how to do this, multiplied by the first derivative with respect to s of s plus p to the mth power times f of s. We close this bracket, close this bracket, evaluated at s is equal to negative p. B to the m minus 2 will be 1 over 2 factorial times the second derivative of that same expression, s plus p times m, or excuse me, to the mth power times f of s, evaluated at s is equal to negative p, and then b to the m minus 3 would be 1 over 3 factorial times the third derivative with respect to s of the same thing, s plus p to the mth power, f of s, close, close, evaluated at s is equal to negative p, and so on. So effectively, if we had a sixth repeated root, we wind up doing a fifth derivative term and all that kind of good stuff, right? So treat this term as if it was the 0th derivative, which is just the function itself. Then we have a first derivative term, second derivative term, third derivative term, so on and so on and so on. Okay. So let's put this into practice. If we have a function f of s is equal to s squared plus 3s plus 3 divided by s plus 3 quantity cubed, what will our inverse Laplace transform of this function look like? Or what does this function look like in the time domain? So hopefully fairly obviously, after partial fraction expansion, this should look like b1 over s plus 3 plus b2 over s plus 3 squared plus b3 over s plus 3, right? So our pole was repeated 3 times, so we should wind up getting 3 terms. Our coefficient b1, excuse me, actually, we're going to start with b3, my apologies. So that's our 0th derivative term. So we're just going to have s plus 3 cubed times f of s evaluated at s is equal to negative p. So that's going to look like s plus 3 quantity cubed times s squared plus 3s plus 3 divided by s plus 3 quantity cubed evaluated at s is equal to negative p. So let's see, that bit's going to cancel that bit. Let me get rid of that negative p thing right there, because we know what numerical value that should have. So what should it be? What number should we be evaluating s at? Negative 3, right? Because s equals to negative 3, what causes this thing to go to 0? So we shouldn't evaluate it at positive 3, we should be evaluating it at negative 3. So in this particular case, that's going to look like negative 3 quantity squared plus 3 times negative 3 plus 3. So 9 minus 9 plus 3 looks like 3 to me. Our coefficient b2 is going to be the derivative of s plus 3 cubed times f of s evaluated at s is equal to negative 3. So really we're just taking the derivative of this part right here that survived, right? So what's that going to look like? Well, I argue it's just 2s plus 3. Evaluated at s is equal to negative 3. And so that's 2 times negative 3 plus 3. So negative 6 plus 3 looks like negative 3, and we call it a day. For coefficient b1, we're going to have 1 over 2 factorial, which is just 1/2, times the second derivative of s plus 3 cubed times f of s evaluated at s is equal to -3. And so now I'm really just taking the derivative of this thing right here from my coefficient 2 determination. So the derivative of 2s plus 3 with respect to s is just 2. So we're going to have 1/2 that term from the very front times 2 evaluated at s is equal to -3 looks like the number 1. Plugging these results in, f of s is 1 over s plus 3 minus 3 over s plus 3 squared plus 3 over s plus 3 cubed. Yes. So I'm always going to have s plus 3 cubed times f of s, which means this bit right here is always going to cancel it out for each thing. So whatever is left over is what I'm taking the derivative of, right? So the 0th derivative of this thing is this thing itself. The first derivative of this thing is this. The second derivative of this thing is the first derivative of this thing, and so forth.
I didn't realize that. So
Every single time. Because this s plus 3 cubed times f of s is inside the derivative operation. Or it's the argument of the derivative operation. So it's going to cancel out every single time. All right, so how do I take the inverse transform of 1 over s plus 3? You guys have a table. I'm sorry, what? I mean, we maybe could. I'm going to do it step by step, and then we'll figure. I'm going to use the linearity property, I guess, of the inverse Laplace transform to figure out what the inverse Laplace transform of each of these parts is, and then I'll factor stuff out as is appropriate. So, going on what North said, though, hopefully fairly obviously, this first term has an inverse Laplace transform of just e to the -3t. Technically, there should be a u of t in there as well. All right, what about our second term? So I have a constant factor of 3 out front, right, that I could get rid of. So to me, this one looks the most like identity number 6, where I would just have 1 over s plus a quantity squared, where a in this case would be 3, and then I could just move that 3 out front. So that would look like 3t e to the -3t u of t. That's my second bit. Anybody got a problem with that? Third bit, slightly more difficult. To me, it looks the most like identity number 7, right? But the numerator doesn't make sense for identity number 7. right? Because if we had let me write identity number 7 down here in blue, right? So when f of t is of the form t to the nth power e to the negative at u of t, its transform is f of s is equal to n factorial over s plus a times n plus 1. Well, in this case, trying to make this guy match what we have here, n would be equal to 2, right? So let me expand this thing out here, right? So we would have 1 over s plus 3. That's something we know how to do the Laplace transform of. And then 3 times 1 over s plus 3 quantity squared. Again, putting it with something we directly know the Laplace transform over. Well, we know the Laplace transform of 2 over s plus 3 cubed, but we don't know 3, so I would just put a factor of 3/2 out here in front to make it look like the right form. So the inverse Laplace transform of this thing right here would be t squared times e to the negative 3t u of t, and that would need to have a factor of plus 3/2 out front. Simplifying things or prettying things up, as it were, we could have e to the minus 3t times 1 minus 3t plus 3/2 t squared u of t. Your whispers. What?
Oh, no, I was using it like we ever have like as
So if we had something with a u of t minus 1, we would expect to have our original function going all the way up here. There would have been an extra term of e to the negative s from because t would be a capital T would be 1 in this case. And so whenever we have this e to the something here, that lets us know that there was a shift in the time domain. So until we see something like this, the short answer is no. In the S domain, a time shift looks like multiplication by e to the negative s times the amount that it was shifted. Any other questions about that? All right. So moving one step further, what if we had a combination of distinct and repeated real poles? So what if our function f of s could be expressed as some function f1 of s times some function f2 of s, where f1 of s was of the following form, where we had some numerator polynomial divided by s plus p1 times s plus p2 all the way out to s plus p sub n times 1 over s plus p to the mth power, right? So we're splitting this up into two functions. One function has discrete real poles, and the second function has repeated real poles. And none of our discrete poles can be the repeated pole. Our partial fraction expansion for this thing would then just be a combination of the two techniques that we've previously developed, right? So we would have something like A1 over S plus P1 plus A2 over S plus P2 all the way out to A sub n over S plus P sub n plus B1 over S plus P, B2 over S plus P squared, all the way out to B sub m over S plus P to the nth power, where the process of determining coefficients A1 through AN is exactly what we saw for distinct real poles, and the process for finding expansion coefficients B1 through BM is the exact same thing as the process for finding the expansion coefficients for repeated real poles. So if we were to work an example, or we are going to work an example, let's use the following function. So let's say that f of s is equal to 2s squared plus 4s minus 10 divided by s plus 6 times s plus 2 squared. For this particular case, we have one distinct pole. So our partial fraction expansion should look like A1 over S plus 6 plus, B1 over S plus 2 plus B2 over S plus 2 squared. So before we jump into calculating coefficients A1, B1, and B2, does this part make sense? We only have one distinct pole, so we should only have one pole factor for that distinct pole. We have a repeated pole that is factor 2, so we should wind up with 2 expansion coefficients for those guys. All right, so how do we find A1? So S plus 6 times f of s evaluated at s is equal to -6. So that would look like s plus 6 times 2s squared plus 4s minus 10 divided by s plus 6 times s plus 2 quantity squared This guy cancels this guy. Evaluated at s is equal to -6. So that's going to look like 2 times -6 squared plus 4 times -6 minus 10, all divided by -6 plus 2 quantity squared, which I got to be 19/8. Process makes sense. That's the important part. The rest of it was just me plugging crap into a calculator. All right. So now we're going to calculate B2 because we always calculate the highest order coefficient for our repeated poles first. So that's going to look like s plus 2 squared times f of s evaluated at s is equal to -2. So we're going to have s plus 2 squared times 2s squared plus 4s minus 10 divided by s plus 6 times s plus 2 quantity squared. This guy and this guy cancels. And we're left with 2 times -2 squared plus 4 times -2 minus 10 divided by -2 plus 6. And I got -5/2. Calculate coefficient B1. We're going to have the first derivative of s plus 2 squared times f of s evaluated at s is equal to -2, right? So we're taking the derivative of what survived when these two things canceled each other out. So to me, that looks like the quotient rule, because I have a polynomial on top and a polynomial on bottom, both functions out, right? So the quotient rule, if I'm remembering correctly, which I don't always do, so please correct me if I'm wrong, would be the denominator minus the derivative of the numerator, excuse me, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Okay. So that's going to look like s plus 6 times 4s plus 4 minus 2s squared plus 4s minus 10 times 1. All of this over s plus 6 squared. And then we evaluate this at s is equal to -2. And I got -3/8. You're nodding your head in agreement, so no questions, just running through, making sure I didn't make a math mistake. Very fair. All right. So now that our three coefficients are determined, we could say that f of s would be 19/8 over s plus 6 minus 3/8 over s plus 2 minus 5/2 over s plus 2 squared. So what should the inverse Laplace transform of this thing be? First two terms should be very easy. Like these should be burned into your head already. So 19/8 e to the minus 6t u of t minus 3/8 e to the minus 2t u of t. All right, what about this next term? Say that again, Daniel. I think you made a slight mistake. I think that's okay. Somebody else take a crack at it? Hannah's got it. Negative 5/2 t e to the negative 2t. And prettying this up, all right, so we have now really laid the groundwork for everything. We just need to look at what happens when the roots happen to be complex numbers. So let's first look at distinct complex poles. And we're going to figure out how this works with an example. Okay. So let's say that we have function f of s is equal to 4s plus 1 divided by s squared plus 4s plus 13. Now it doesn't really look like it in this particular form, but we actually know everything we need to take the inverse Laplace transform of this thing as it stands. And we'll burn through that in just a moment. But what we're going to find out is that our result is going to be the sum of some sinusoidal functions. And as electrical engineers, we know that anytime we have the sum of sinusoidal functions with the same frequency, there's probably a way to cram it all into a single sinus, right? So let's burn through the method that would get us the sum of sinusoidal functions here really quickly. Okay. So I could treat this as if it were 4s plus 1 divided by s squared plus 4s plus 4 plus 9. Let me come down here. So for my denominator, that would look like s plus 2 quantity squared plus 3 quantity squared. And so looking at that denominator, would not be super obvious why you would ever think of that thing as this thing. What kind of things would we want our numerator to look like, right? So I have an S plus A quantity squared plus some omega quantity squared down here in my numerator. So I'm looking at identities number 8 and 9. Actually, I'm looking at more like numbers 12 and 13 because I have the S plus A, right? So to make this fit more in the mold of those identities, I'm going to expand my numerator. So I'm going to have this as 4s plus 1 plus 7 minus 7. So if I add anything, I have to subtract anything. And that's going to give me 4 times s plus 2 over s plus 2 squared plus 3 squared, which we can find the inverse Laplace transform of. And now I would have minus 7 over that same denominator, but I don't like that because I'm expecting to have omega over s plus a quantity squared plus omega squared. So to fix that, I'm going to call this thing negative 7/3 times 3 over s plus 2 squared plus 3 squared. To put it in the form of something I know the inverse Laplace transform of. So now, from here, f of t would be 4e to the negative 2t cosine 3t u of t minus 7/3 e to the negative 2t sine 3t u of t. There is nothing technically wrong with this, but it's not in the most compact form we could find. Yes. Four s plus 8. Factor out 4. Over here. Negative 7/3 times 3 is negative 7. Yep. We got to get creative for sure in order to make these things fit. But it is possible if we do weird completing the square things and all that kind of jazz. And if you know what to look for, you can make this weird thing fit a couple of things that we already know. But there is a way to make it come out with an answer that doesn't involve all of this algebraic wizardry or black magic or whatever the hell you want to call it. Okay. So let's talk about that thing. This is the second order polynomial, right? So we can use the quadratic function to figure out what the roots of this thing are. So somebody do that 8th grade math and tell me what these roots should be. All right, so we're looking at this thing right here, and we should get 2 values for s, okay? So negative b, negative 4, plus or minus the square root of b squared, minus 4 times 13, because a is just 1, divided by 2, which should look like negative 2 plus or minus J3, I believe. I got the over 2-bit already taken care of. divided by 2. Yep, nope, not a. So that means that this function could be expressed as f of s will be equal to b1, where this expansion coefficient could be a complex number, which is why I'm putting a bar over it. S plus 2 minus J3 plus B2 over S plus 2 plus J3. So that these values of S are what cause these denominators to go to 0. So are we very clear on why if we have a -2 here, we have to have a +2 down here? Because the S has to cancel this business out. All right, so these are distinct poles. Which means we can just use the method that we had for distinct poles. So coefficient B1 is going to be S plus 2 minus J3 times f of s evaluated at s is equal to -2 plus J3. Yes. We don't have repeated poles here, so it really doesn't matter which one I do first. I'm never going to do a derivative here. Now we're going to get to something. We'll get to that in a minute. We got to figure some stuff out. All right. So I have, yes. Because I need this value of S to make this thing look like 0. So whatever value of S makes this look like 0 is what I'm evaluating it. So in order to cancel out the +2, I need the -2 in the real part. In order to cancel out the -J3, I need the +J3 in the negative. So S plus 2 minus J3 times my numerator, which at this point I've lost it. Let's see, 4S plus 1. Over S plus 2 minus J3 times S plus 2 plus J3. Evaluated at S is equal to -2 plus J3. This guy cancels this guy. And evaluating this at this particular value of S gives me the following complex number in polar form, 2.315 angle positive 30.256 degrees. Like I said, our expansion coefficient B1 could wind up being a complex number when we have complex conjugate roots here. So just finding B2, we would have S plus 2 plus J3 times f of s evaluated at s is equal to -2 minus J3. So S plus 2 plus J3 times 4S plus 1 divided by S plus 2 minus J3 times S plus 2 plus J3. Evaluated at S is equal to -2 minus J3. This guy cancels this guy. And we wind up getting 2.315 angle negative 30.256 degrees. What's the relationship between B1 and B2? They're conjugates of each other. So effectively, anytime that our roots are conjugates, our expansion coefficients are going to be conjugates as well. So realistically, we never actually have to solve for B2. It will always be the conjugate of B1. So from this, we could say that f of s is equal to 2.315. I'm going to express this number in exponential. You'll see why in a moment. Literally, all I am doing is taking the magnitude and then putting this angle as e to the j angle, because polar form and the exponential form literally have the same information. They're just expressed in slightly different ways. 30.256 degrees divided by s plus 2 minus j3 plus 2.315 e to the negative j, 30.256 degrees over s plus 2 plus j3. And so in the time domain, this is going to look like 2.315 e to the j, 30.256 degrees times e to the negative 2 minus j3 t u of t plus 2.315 e to the negative j, 30.256 degrees e to the negative 2 plus j3 t u of t. Now, you may be wondering to yourself, how the hell does this look any better than the thing we got earlier? And the short answer is that right now it very much doesn't. Okay. So what I'm going to do is I'm going to play around with the fact that I have exponential functions multiplied by exponential functions, right? So, for example, I could write this as 2.315 e to the negative 2t, where I'm getting that e to the negative 2t from this part right here. So I have e to the negative 2 times t times e to the j. So I have negative times negative, so that's going to give me a positive j here times 3 plus 30.256 degrees. U of t plus 2.315 e to the negative 2t e to the negative j, 3t plus 30.256 degrees U of t. So if I take the negative j out here, I get positive 3. If I take the negative j out here, I get positive 30. So I wind up getting the same argument on both sides. Now, rearranging things a smidge here, I have a common factor of 2.315 e to the negative 2t. Here in the middle, I'm going to have e to the j, 3t plus 30.256 degrees plus e to the minus j 3t plus 30.256 degrees u of t. What does this thing here in the middle make? All right. Let's run through some things here. Again, this is the, I think, third time in this class. E to the j x is equal to cosine x plus j sine x. E to the minus jx is equal to cosine x minus j sine x. And if I add these things together, I have e to the jx plus e to the minus jx is equal to twice cosine of x. So this part right here looks like twice cosine 3t plus 30.256 degrees. Putting this all together, we are going to have 4.631, if I'm not mistaken, because of rounding error. Yeah, 4.631 e to the negative 2t cosine 3t plus 30.256 degrees u of t. That's our final limit, which is in a more compact form than the sum of our exponentially decaying sinusoids that we saw earlier. Now, let's make an identity out of this so that we never have to do it again. Okay. Do what now? This bit right here. So this cosine 3t right here, we could have turned that into 1/2 e to the j 3t plus 1/2 e to the negative j 3t. This sine function right here, we could have turned that into 1/2 e to the j 3t minus 1/2 e to the j negative 3t. And then, yeah, we probably could have done manipulations, a similar amount of manipulations to cram this into a single function. But that doesn't help us make an identity for the Laplace transform we're divided into. So our identity is as follows. If f of t is of the form e to the negative at cosine omega t plus some phase angle theta, f of s will be equal to 1/2 times e to the j theta divided by s plus a minus j omega plus e to the negative j theta divided by s plus a plus J omega. So that if we have a function, and the denominator is of second order, right? And the roots of that second order polynomial are complex conjugates of each other, we know that we're going to wind up having an exponentially decaying cosine function as our result. So the last thing that we need to look at then is what happens if we have repeated complex roots. Yeah, you're gonna be angry about this. By the way, this identity here should go in slot number 15 on your page if you haven't already written it down. All right. Repeated complex poles. So once again, we're going to look at what the heck. All right. We're going to look at an example to figure out how this thing is going to work. So let's say that we have the following S domain function 108 times S squared plus 2 divided by S squared plus 10S plus 34 quantity squared. What are the poles of this thing going to be? Oh. Using our good old quadratic formula, we're going to have -10 plus or minus the square root of 100 minus 4 times 34, all divided by 2, which to me look like -5 plus or minus. Sorry, I'm having a lot of input lag on my stylus right now. J3. So that this thing could be expressed as S plus 5 minus J3 squared times S plus 5 plus J3 squared. And then my numerator is just going to say the same. All right. All right. Actually, I think I'm going to stop here because my computer needs to be restarted so that this stops lagging. And by the time it's done doing that, we're going to be out of class time. So we'll kick off Wednesday's class meeting, figuring out how the heck this thing works. By the way, it's going to result in the identity for number 16. And then we're going to get along with circuit analysis in the S domain. I would expect your next exam to be the following Friday. So that would be Friday the 20th. So circuit analysis in the S domain, circuit analysis in the S domain, probably wrapping up circuit analysis in the S domain, one or class meeting to a class meeting and a half of synthesizing things, and then your exam. So that seems like a reasonable place. Yes, so that's a fantastic question. So for this upcoming exam, you will get this sheet except that I will actually be nice enough to fill out all of it for you, not just parts of it. Yes, so that will be your equation sheet for exam 2. All right, thank you guys.